Hello everyone, welcome back to another Eviews video tutorial. My name is Juan and today I'm going to be talking about GARCH models in Eviews. For those of you who are watching this tutorial for the first time, I want to let you know that I have another tutorial where I talk about ARCH models. It's very important that you watch that tutorial first because these two videos are interconnected and it's going to be helpful for you to understand the difference between ARCH and GARCH and how to estimate both models. There is a link in the description where you can buy the slides along with the Eviews Word file and the dataset. And there's also another link where you will be able to download the dataset for free for you to replicate the content that we are covering in this tutorial. So let's begin. Let's start by an overview of GARCH models. GARCH stands for generalized, autoregressive conditional heteroskedasticity. The model is an extended version of ARCH models and it was introduced in 1986 by Vollerslev. GARCH model allow us to model the conditional variance as an ARMA process. They incorporate autoregressive and moving average components in the heteroskedastic variance. What are the benefits of this type of models? Well, GARCH models provide a parsimonious alternative to high-order ARCH models. As we have seen with ARCH models, one of the flaws of ARCH models is that if it incorporates many ARCH effects, then you're going to be having problems with estimating those type of models when you are incorporating so many ARCH terms. Then some of them may become not significant or some may become negative, and those are all things that we don't want in our ARCH model. So GARCH are always a good alternative to high order ARCH models. Let's go now through the formalities. Now in the case for GARCH, we have both terms, P and Q, where in ARCH you only had the P term. Once again, here we have our mean equation. In this case, we have YT, which is going to be explained. In this case, it's just a simple autoregressive model with past values of my variable Y. But we have that in the error term, it's a normal distribution, the previous information, but this HT terms means for heteroskedastic. So it's not a constant variance, it's going to be changing over time. And the way that we are going to be modeling this variance is by including the ARCH terms on the first part, but then including also the MA terms in the second part of the variance equation. And the following things have to be satisfied. Well, we have to ensure that all the terms alpha 0 and all the alphas that we are going to be incorporating, these alphas stand for, remember, the ARCH terms. If we include 1, 2, 3, 4, all those ARCH terms have to be positive. And also the beta, beta 1, beta 2, beta 3, however many terms GARCH you include, then they have to verify that are positive terms. And the reason for this is to guarantee a positive variance. And the next thing that you have to ensure is that when you add the AR terms with the MA terms in the variance equation, that has to be smaller than 1, and that is to have a decaying variance over time. So those are some of the things that we need to ensure when we are estimating our GARCH models. All of the terms have to be positive, and when we add up the ARCH and GARCH terms, it has to be smaller than 1. So what are the steps to estimate GARCH models? Well, the first thing that we need to have is a model for the mean equation. You can do this by estimating an ARIMA model. Then from the mean equation that we are estimating, we need to test for the existence of ARCH and GARCH effects. If the test confirms the existence of ARCH-GARCH effects, we are going to re-estimate our model, including the appropriate ARCH and GARCH components. So large ARCH models can be better identified by a GARCH 1-1 model. So normally a GARCH 1-1 will satisfy our variance equation. And finally, we are going to be conducting some diagnostic tests. So what are we looking for? Well, we need to ensure that our specification mitigates heteroskedasticity. So recall that the reason why we are including these ARCH and GARCH effects is to be mitigating that our variance that is changing over time. So in other words, if there is still heteroskedasticity in the model, your specification is poor and you need to incorporate more ARCH-GARCH terms. For today's example, I have Microsoft returns. We're going to try to fit a GARCH model for the returns of the Microsoft stock. In the blue line, you can see the evolution of the price of Microsoft stock. And here in the orange line is showing us the returns of Microsoft stock. So we can see that in 2020, there has been a significant drop at the beginning of 2020 due to COVID, and this is something that we will try to incorporate in our GARCH model. So how are we going to do this? Well, we're going to first start with our mean equation. Before checking for the existence of ARCH or GARCH effects, we should estimate our mean equation. So I'm going to show you this in Eviews, and what you will be able to determine is that from the correlogram of the returns of Microsoft stock, we will be able to fit an ARMA 1-1 model. So let's get into Eviews now, and let's try to estimate the mean equation. In Eviews, I have included in the dataset other type of stocks as Amazon, Apple, Netflix, Nvidia, so you can download this dataset and practice. But let's get into Microsoft now. That is our example for today. I'm going to double click on the variable and see the graph. I'm going to click on View Graph. And here we get our graph for the Microsoft stock. You can see the evolution of the stock over time. However, to look at the returns, I'm going to click on Default here, but I'm going to change it to Log and Differences. So this is the graph that is going to show us the returns. So let's generate then a variable. I'm going to click Generate. And we're going to generate the returns of the Microsoft stock. I'm going to type returns equal. And now I type differences and log of Microsoft. So here I have generated the variable. I'm going to double click on returns. I'm going to click on view, graph. And now you can see that this is exactly what we have just looked at previously. This is our variable now that we have generated the returns. So it's important now to try to fit the mean equation. So I'm going to go into view, correlogram. We're going to see a correlogram in levels. And recall from my ARIMA tutorial, for those of you who haven't watched that tutorial, I would like to invite you to take a look at that video. So then you can see that with the autocorrelation and the partial correlation, we will be able to determine how many AR and MA components we are going to be including in our model. For all of those bars that are exceeding the confidence bands, those could be potential candidates to estimate the ARIMA models. In this case, I'm just going to keep it simple, and I'm going to estimate a parsimonious model. So I'm going to just be using the first two components. I'm going to estimate an ARMA 1-1 model. So we're going to go into quick, estimate equation, and I'm going to type returns. Then I'm going to type a constant, AR1, and an MA1 term. We hit enter, and here we have our model estimated. So let's see what is the next step. So now that we have our mean equation, we need to check for the existence of ARCH effects. So we're going to conduct the heteroskedasticity test and select the ARCH option. The null hypothesis is that there is no existing ARCH effects up to the lag that we have specified, and the alternative hypothesis is that there are ARCH effects up to that specified lag. As a hint, if the p-value is smaller than 5%, we're going to reject the null hypothesis and confirm the existence of ARCH effects. To do so in Eviews, I'm going to go into View, then I'm going to hit in the Residual Diagnostics, Heteroskedasticity Test, and select the ARCH option. From here, we are going to just leave as a default a 1, and I'm going to hit OK. And you can see then that the p-value here is telling us that it's smaller than the 5% significance level, so we are concluding then that there exist ARCH effects. And you can see that the first residual, so adding one ARCH component, is appropriate since the p-value is smaller than 5%. So how can we determine then how many ARCH effects we're going to include? Well, I have talked about that in my ARCH videos, but I'm going to just show you quickly that you should go into View. We are going to go into Residual Diagnostics and select the option Square Residuals. So looking at the square residuals, here I'm just going to type 10. Looking at the square residuals, the partial correlation tab can give you an idea of how many ARCH effects you can fit. And you can see that there are first two terms that look right away, that look statistically significant. The third ARCH term doesn't seem to be appropriate, and then the 4 and 5 term could be included. However, as I mentioned before, we don't really want to add so many ARCH effects. Okay, so let's re-estimate now our ARCH test, and let's include two residuals, as is suggested in this partial correlation section. So I'm going to go into view. I'm going to go into residual diagnostics and select heteroskedasticity test. We're going to select the ARCH option, and we're going to be including two lags. So now when we include two lags, we can see that both lags, the first residual and the second residual, are statistically significant. They are smaller than 5%. So including these two ARCH effects are going to be appropriate. And what's more, what we can do as well is we can try with three. So I can show you that the third one is not significant. So I'm going to go into heteroskedasticity test, ARCH effects, and I'm going to include three lags now. So when we include three lags, what you can see clearly is that the third lag is not significant. And if you remember the square residuals, I'm going to show you again. I'm going to go into residual diagnostic, square residuals. Let's go just with 10. We don't need so many lags in my graph. You can see that the third term is not appropriate, right? So that's what it's telling us, basically, our results from the heteroskedasticity test. Including two ARCH effects will be fine. So let's try to estimate this ARCH 2 model, and then let's estimate a GARCH model and compare both. Which one fits better Microsot returns? An ARCH 2 or a GARCH 1.1? So as I just mentioned, let's try to first fit an ARCH model before estimating our GARCH model. So the mean equation, we have already determined that we are going to be including a constant, an AR1 term, and an MA1 term. So let's add the two ARCH effects to this model. Let's go into views and estimate it. In Eviews, we're going to go into quick estimate equation. And from here, you're going to change the estimation method, and you're going to be selecting in Eviews. To estimate this equation, I'm going to go into quick estimate equation, and it's very important that you change the method to ARCH. So you see that when you click ARCH, a different window appears, and the first box is asking you to explicit what is your mean equation. And we have already determined that my mean equation is going to be returns, a constant, an AR1 term, and an MA1 term. And the next thing that we're going to do then is I'm going to change this GARCH 1 to, we're going to not include any GARCH terms, and we're going to be including the two ARCH terms that we have just mentioned. So I'm going to hit OK. And now what you can see from this model is telling me that my AR1 term is statistically significant, my MA1 term is statistically significant, and what's more, my two ARCH effects, the ARCH effect 1 and the ARCH effect 2, is appropriate. The next thing that we should be doing now is asking if this model is appropriate or not. So what we should determine now is that with including two ARCH terms, there is not going to be any more heteroskedasticity. Because if there is, what the model is telling you is that the two ARCH terms is not going to be sufficient to mitigate the heteroskedasticity in the model. So I'm going to go into view, residual diagnostics. We're going to do again the ARCH test. We're going to change this to 2 because we have included two ARCH terms, as you can see. And as I mentioned, we have to determine that there is no heteroskedasticity in this model. So now what you can see is that including the two ARCH terms, we can see that we are rejecting now my hypothesis. We are not rejecting my hypothesis of no heteroskedasticity. So then this is good. We have determined that including two ARCH terms is going to mitigate heteroskedasticity. But now let's try to estimate a GARCH model and see how the GARCH model does in comparison to this ARCH model. Before moving into the GARCH estimation, here I have included how you would be writing the equation. So you would have your Microsot mean equation, okay? And then what you would have is your variance equation. And the variance equation is including the two values for the ARCH terms. So what you can see is that remember that as a requirement that the both terms had to be positive, and you can see that these two terms, okay, these two terms are positive. And the second thing that you have to ensure is that adding these two terms is not going to exceed 1. And you can see that if we add up these two terms, you're going to get to 0.55. 0.55 is smaller than 1, so then we are fine. This model satisfies the requirements that we had established at the beginning. So what you can see is that the variance adds to 0.55, and what you should know is that the closer that this value is closer to 1, then the volatility is going to be higher. So 0.55 is in the middle, and as I mentioned, if it was closer to 1, that's going to say that the volatility periods are going to be very persistent. So now let's move into the GARCH estimation. Often GARCH 1-1 models can be a good alternative to high-order ARCH models. GARCH models are simple and robust models for volatility. There can be diverse order specification, for example, a GARCH 2.2, GARCH 3.3. However, higher orders of GARCH models are often estimated when you are using long span of data, like for example, several decades or of daily data, or a year of hourly data. So you can find more details in a paper I include in the description that is written by Engel in 2001, where he's basically providing more details on when a GARCH model is more appropriate. So I highly encourage you to read this paper. So now let's estimate the GARCH 1-1 model to see how it does in comparison to the ARCH model. To estimate my GARCH model, I'm going to go into Quick, Estimate Equation, and I'm going to type here, I'm going to first select, the option ARCH, and we're going to type here returns. We're going to select a constant, an AR1 term, an MA1 term, as we have determined the mean equation before. And now we are allowing for GARCH terms. We're going to use an ARCH1 and a GARCH1 term. So I'm going to select OK. So now here we have our GARCH 1-1 model. You can see that with the GARCH models as well, my mean equation, the AR1 term and the MA1 term are appropriate, the p-values are smaller than 0.5, but also you can see that both the ARCH and the GARCH term are statistically significant. So both including this GARCH 1-1, it looks like it's a good model. We can go into view and we can do now the ARCH test to see if there is heteroskedasticity still. And you can see that there is no heteroskedasticity anymore when we are using our GARCH model. We are now confirming that also a GARCH 1-1 model mitigates the heteroskedasticity that there existed in my model. So now you are questioning, okay, so what model are we going to use? Which one is better, an ARCH or a GARCH model? So let's take a look into the next slide to see how we're going to determine that. So we are going to be comparing the ARCH and the GARCH models using the following criteria: the log likelihood, the Akaike, the Schwartz, and the Han-Quinn. On the first column here, we have the ARCH 2 model, and in here we have the GARCH 1-1 model. So the log likelihood, since we are maximizing the log likelihood, the one that has the bigger value is going to be preferred. So if we compare these two values, the model B is bigger, so we're going to select model B. Now when we move into the Akaike, Schwartz, and Han-Quinn, we have to select those values that are smaller. Since our values are negative, the smallest values are going to be the most negative, let's put it that way. So you can see that this value, then model B is going to be preferred over model A. Model B, looking at the Schwartz criterion, is going to be preferred over model A. And then looking at Han-Quinn, my model B is going to be preferred over model A. So we have determined then that my GARCH 1-1 model has better properties than using the ARCH 2 model. So now the last thing that we can do is graphing the variance equation. In order to graph our conditional variance, I'm going to go into Proc, make GARCH variance series, and I'm going to call it just GARCH1 is fine. And here we have the series. The next thing we are going to go is into View, Graph. We're going to leave it as line and symbol and hit OK. So here we have our conditional variance graph. So that's going to be all for today. I hope you found this video useful and that it helps you to understand the difference between an ARCH and a GARCH model and how to select between an ARCH and a GARCH model as well. I would like to invite you to subscribe to my channel if you would like to get more content related to applied time series analysis, forecasting. All of the topics that I cover are related to economics, and I trust that these are going to help you if you are taking econometric courses or time series analysis or you're writing a research paper. So once again, I would like to thank you very much for all your support, for watching my tutorials. And for those of you who are buying my material, that's great. It does help me a lot to keep creating more content. So thank you very much. And well, let's keep tuned for my next video. Take care.